This is a summary video for the AQA Trilogy specification for the C2 bonding, structure and properties of matter topic. In this unit, we look at how different substances bond together and how the type of bond determines the property of a structure. Going back to our periodic table then, I'm sure in the past your teacher will have shown you how to draw the steps starting at aluminium, going down the periodic table, and that when we've drawn this step, the elements to the left of the step are all metals and the elements to the right of the step are all non-metals. In chemistry there are three types of bonding. The first is ionic bonding, which is bonds formed between a metal and a non-metal atom. Then we have covalent bonding, which is formed between non-metal atoms. And finally we have metallic bonding, which is formed between metal atoms. So why does bonding happen? Well, atoms with incomplete outer shells are unstable, and they react with other atoms to gain, lose or share electrons and obtain a full outer shell to become stable. Let's start then by taking a look at ionic bonding. A reminder, ionic bonding is the bond formed between a metal and a non-metal. So ion, key definition, is a charged particle, can be positive or negative, and it is formed when atoms gain or lose electrons. Something we need to remember. A sodium atom then will have 11 protons and 11 electrons. Protons are positive, so it has a plus 11, and the electrons are negative, so it has a minus 11. If we add those up, overall we have zero charge. However, we have a partially full outer shell, and this means that the atom is unstable. The easiest thing for sodium to do then is to lose this one electron that it has in its outer shell. This now means that it has 11 protons still, because it's still sodium, and if we change the proton number we change the element. But now it only has 10 electrons because it's lost one, and if we add our charges up now we get a charge of +1. We tend to draw ions in square brackets and we put the charge outside of the square brackets. Here we can see that its outer shell is full and this ion is now happy. Let's then have a look at a group 2 element. Let's look at magnesium. So magnesium has 12 protons and 12 electrons. If we add up the charges of both of those, a magnesium atom has 0 charge, but it does have 2 electrons in its outer shell. So if it loses those 2 electrons to gain a full outer shell, it now has 12 protons but only 10 electrons. If we add up the charges for those then, a magnesium atom would have a charge of +2. An atom that gains one or more electrons forms a negative ion. It's gaining negativity. Elements from groups 5, 6 and 7 will gain electrons to get full outer shells. And if we go back to our periodic table, we can show our positive metal ions, and then non-metals form negative ions. So we've got -3, -2, -1. Group 4 do not form ions, and group 0 already have a full outer shell, so do not lose or gain electrons. Let's look at a fluorine atom then. Fluorine has 9 protons and 9 electrons. Overall it has a charge of 0, but it has a partially full outer shell with 7 electrons in its outer shell, so it's not happy. It therefore gains 1 electron, and now it has 9 protons and 10 electrons. and we add this up, this gives us a charge of -1. So when fluorine gains an electron, it forms a fluoride ion. Note the difference. As an atom, it's a fluorine atom, and as an ion, it's a fluoride ion. That's something to be careful of when you're writing about this. But now it has a full outer shell and a -1 charge. Let's then look at oxygen. Oxygen has 8 protons and 8 electrons. You can see that it has 6 electrons in its outer shell, and indeed oxygen is found in group 6 of the periodic table. Ideally, oxygen would like to have 8 electrons in its outer shell, and it does this by gaining 2 electrons. This gives it a full outer shell, but it also means that it then has a charge of -2, because you can see that it's got 8 protons and it now has 10 electrons. Just like to point out that when negative ions are formed, the name changes, so the oxygen atom becomes an oxide ion, so they end in "ide", and on the previous slide we saw fluorine becoming fluoride. So when negative ions are formed, their names change. But that's not the whole story. We've talked about atoms gaining and losing electrons, but you can't just find electrons and you can't just lose them. So it needs 2 elements to react together, and in the case of ionic bonding, it will be a metal reacting with a non-metal. The metal will lose electrons and the non-metal will gain electrons. This then produces 2 oppositely charged ions, and they become electrostatically attracted to each other and form an ionic bond. This will also produce a compound. First of all, let's look at the bonding in sodium chloride. When we have a sodium atom and a chlorine atom, the sodium atom has 1 electron in its outer shell, and the chlorine atom has 7 electrons in its outer shell. Here it's quite straightforward. Sodium wishes to lose 1 electron and chlorine wishes to gain 1 electron. So the outer electron from sodium is transferred to chlorine. We now have a sodium ion and a chloride ion. The sodium ion is positively charged and the chloride ion is negatively charged. These oppositely charged ions would attract each other through the electrostatic force of attraction between the oppositely charged ions. This is the ionic bond. Ions, however, are not 2-dimensional. They exist in all 3 dimensions. So the positive and negative charge will be applied in all 3 dimensions. Ionic compounds will consist of more than 1,000 ions, and these are joined together by ionic bonding to form a 3D lattice. Let's now have a look at magnesium oxide then. So as you'll know from your periodic table, magnesium is in group 2, so it has 2 electrons in its outer shell, and oxygen is in group 6, so it has 6 electrons in its outer shell. So here we have magnesium, which wishes to lose 2 electrons, and oxygen, which needs 2 electrons to gain a full outer shell. So in this case, 2 electrons are transferred from magnesium to the oxygen. This will leave the magnesium ion with a +2 charge, and the oxygen atom has now gained 2 electrons and becomes an oxide ion that has a -2 charge. And just in the same way that sodium and chlorine reacted, Here we've got the magnesium ion and the oxide ion that are oppositely attracted. So the electrostatic force of attraction between the oppositely charged ions occurs, forming the ionic bond. And in exactly the same way as the sodium chloride, these ions are three-dimensional, and this will happen in all 3 dimensions, forming a giant 3D lattice. So going back to sodium and chlorine, the sodium loses its outer electron and chlorine gains it. The result is that both of the elements end up with full shells and become ions. These ions are oppositely charged, so the 2 oppositely charged ions that are formed attract each other, and the ionic bond is the electrostatic attraction between oppositely charged ions. Let's then look at covalent bonding, and covalent bonds are formed between non-metal atoms. So when 2 non-metals bond with each other, the atom doesn't lose or gain electrons, they share electrons. And you can see here I've got 2 hydrogen atoms, each with 1 electron in their outer shell. And when they bond, those outer shells overlap and they share their outer electrons. The shared electrons in the overlap will count towards the total number of electrons in the outer shell for both atoms. So how is the bond formed then? Well, the bond is the electrostatic force of attraction between the shared pair of electrons, that's the electrons in the overlap, and both the positive nuclei. Well, let's look at the bonding in chlorine. Chlorine is a group 7 element, sometimes referred to as halides. This means that it has 7 electrons in its outer shell. If a chlorine comes near another chlorine, both of them have 7 electrons in their outer shell. This means that they are going to covalently bond by sharing the single unpaired electron that each of them have in their outer shell. You can see from the diagram that there are 2 electrons in the bond. So a covalent bond is 1 shared pair of electrons. This molecule would be a Cl2 molecule, or we could draw it as Cl with a horizontal line and another Cl. The horizontal line indicates a single covalent bond. If we now look at oxygen, oxygen is in group 6 and has 6 electrons in its outer shell and requires another 2. So in this case, the oxygen atoms will each share 2 electrons. So there are 2 shared pairs, and this is a double covalent bond. And you can see that shown by the 2 horizontal lines. Finally then, if we look at nitrogen, which is in group 5, nitrogen needs 3 more electrons. So nitrogen. Covalent bonding can also occur between atoms of different non-metals to create molecules of covalent compounds. So in this example here, I've got hydrogen and chlorine. Chlorine would like to gain another electron to get its full outer shell, as would hydrogen. So in this example, they will share 1 electron. In the case of carbon dioxide then, carbon has 4 electrons in its outer shell and needs to share each of those. It does so in carbon dioxide by sharing 2 electrons with each oxygen atom. So it forms 2 double bonds, 2 shared pairs of electrons with each of the oxygen atoms. and we would see that written as a C with 2 double bonds, one either side, going to each oxygen atom. Let's now look at metallic bonding. A reminder that metallic bonding is formed between metal atoms. So here we have magnesium. Magnesium is in group 2, and this means that magnesium has 2 electrons in its outer shell. When magnesium atoms bond and form magnesium metal, they lose these outer 2 electrons. Their outer electrons become delocalized, so they're still there, they're just not attached to the magnesium ion. These free electrons from the outer shell of the metal atoms are what helps to form the metallic bond. The metallic bond is the electrostatic force of attraction between the delocalized electrons and the metal cations. We've looked at how different atoms bond together. We now need to look at how that bonding influences the properties of the substances and how the structures are formed. First of all, let's remind ourselves of the particle model. Starting with solids. Solids cannot be compressed. Solids will keep their shape, and solids are strong. Do you think the forces between particles in a solid are weak or strong? That's right, they are strong. So we have strong forces between the particles in a solid. If we then look at liquids, remembering that liquids cannot be compressed because their particles are still close together, but their particles are able to move, so liquids can flow. What do you think this means for the forces then? Are they weaker or stronger than a solid? They are weaker than a solid, and this is what enables the particles to be able to move. Let's look at gases then. So they can be compressed easily because there are gaps between the particles and their particles are very spread out. Gases can also flow. What does this mean for the forces between the particles in a gas compared to those in a liquid? Well, they will be weaker than those in a liquid. We can represent physical states of solid, liquid and gas in chemical equations by using state symbols. So we have S for solid, L for liquid and G for gas. We also have a fourth state symbol, which is AQ. This is an aqueous solution and represents that something has been dissolved in water. You can see in this equation I've got solid sodium reacting with liquid water to form an aqueous solution, so that means the sodium hydroxide that's formed will be dissolved in the water and also producing H gas, which I would see given off as bubbles. Let's start then by looking at the properties of ionic substances. That's substances that have got bonds between metal and non-metals. And a reminder then that a positive metal ion will be electrostatically attracted to a negative non-metal ion, and that this happens in all directions. Here we have two diagrams that are often used to represent ionic compounds. Sometimes you may be asked what the problem with using such simplified models is. With the diagram on the left, this would imply that there are gaps between each of the ions. This is incorrect. The ions will always be touching in all directions. So the giant ionic lattice has strong electrostatic forces of attraction in all directions between the oppositely charged ions. As we've seen, ionic compounds exist as 3D lattices with many strong ionic bonds. It will take a lot of energy to be able to break these ionic bonds, and because of this, ionic compounds have very high melting points, and at room temperature will exist as a solid. Let's now have a look at the physical properties of ionic compounds. First of all, I'm going to start with something that isn't an ionic compound, the substance copper. Copper is a metal. What we're going to look at here is a circuit where we can put the substances into the circuit and see whether or not they conduct electricity. Now, we all know that copper conducts electricity. So if I put copper into the circuit and I turn the circuit on, the bulb lights up. As you will see in a few lessons' time, when we look at metallic bonding, the reason that copper conducts electricity is because it has a sea of delocalized electrons that allow the current to flow through the structure and hence conduct electricity. But we want to look at ionic compounds. So first of all, I'm going to start with sodium chloride. So this is table salt. And if we turn on the circuit, you can see that the light bulb does not light up. And this is because solid ionic substances do not conduct electricity. There are no ions that are free to move, and there are no delocalized electrons. Everything is tightly bonded together in a 3D lattice. This, however, is not the case when we look at sodium chloride solution. If we put sodium chloride solution into the circuit and turn it on, you can see that in this case the light bulb lights up. And this is because once we have put an ionic substance into a liquid form, and that could be dissolving it in water or it could be just melting it so it is a liquid, then the lattice becomes disrupted and the ions break away. These ions are then free to move, and as they are charged particles, they can carry the electrical charge through the substance, and hence liquid ionic compounds will conduct electricity. Summarising then what we've just seen in the video. Here we have the picture of an ionic solid. As a solid, the ionic substance will not conduct electricity. This is because the ions are not free to move and carry the charge. However, once they become a liquid and the particles can move, and that could be either as a molten solid, so we've just heated it up till it melts, or we could dissolve it in water. Once the ions are able to move, then they will conduct electricity because the ions can move and so the charge can flow. Let's now then look at the properties of covalent substances, remembering that covalent substances are formed between non-metals. So here we have a picture of ammonia, and you can see that the covalent bonds are shown by the lines between the nitrogen and the hydrogen atoms. But we also now have intermolecular forces, and these are the forces that will exist between all atoms. So the amount of energy needed to change a substance from a solid to a liquid will depend on the strength of the forces between the particles of the substance. If this intermolecular force is weak, then it will take very little energy and the substance will have low melting and boiling points. If the force between the molecules is strong, then they will have a lot of energy needed to be able to turn them to a liquid or a gas, and therefore they will have high melting and boiling points. It is important that we remember that the bonds inside a molecule, so the intramolecular force, the bonds are very strong, and even in small covalent molecules, the bonds between atoms within a molecule are very, very strong. However, the intermolecular force between the different molecules can be weak, and in this case these are small molecules and they will have weak forces between the molecules, so they have weak intermolecular forces. The bonds inside the molecule are very strong. Covalent bonds are incredibly strong bonds. When we make a substance change state, we do not break any chemical bonds. I always like to think of this as in terms of oxygen. So when we breathe in the gas O2. That's a molecule of 2 oxygen atoms covalently bonded together. It's a gas, but it's still a molecule. So we only break the forces between molecules, the intermolecular forces. And if we look at group 7, we can see that for each of the halogens, as you go down the group, the molecule gets bigger. And that means that as the molecule gets bigger, the melting and the boiling point increases. We look at the physical states of them then. Fluorine and chlorine would be gases, bromine is a liquid, and iodine is a solid. To summarise then, we can say the bigger the molecule, the higher the boiling point. And there's 2 reasons for this. The amount of energy needed to make the molecule vibrate will be bigger if the molecule is bigger, and also the bigger the molecule, the bigger the intermolecular force. Let's look at the properties of metallic substances, reminding you that metallic bonds are formed between metal atoms. These are giant structures, and as we've seen before, things that have giant structures have high melting and boiling points, and this is because they have many strong bonds. That means that it will require a lot of energy to break all of these bonds, so therefore metals have high melting and boiling points. The exception, of course, to this is mercury, which is a liquid at room temperature. Metals can often be described as being malleable. This is because their atoms are arranged in layers, that the layers can easily slide over each other, which means that they can be bent easily. That is what malleable means, they can be bent. Metals are excellent conductors, and the reason they are is because they have the free delocalized electrons that can move through the structure and carry electrical charge. Let's now look at polymers. Polymers are a special type of substance that are usually formed out of long chains of carbon atoms. Polymers are very long molecules, and they're made from lots and lots of carbon atoms joined together. As you can see from the diagram below, the carbon atoms are joined together with single covalent bonds, and then they have hydrogen atoms coming off them. Each carbon makes 4 bonds in total, and a carbon chain can be over 100 carbons long, and sometimes even thousands. Thermal softening versus thermal setting then. Thermal softening plastics will soften when you heat them and you can reshape them, whereas thermal setting plastics do not soften when they are heated, and they are used when you need something that's resistant to heat. If you notice here, there are bonds between the chains. These are called crosslinks. Whilst carbon can form simple molecules such as carbon dioxide and methane, it also has the ability to form giant covalent structures as its element. So carbon, the element, can exist as diamond, or it can exist as graphite. Okay, so previously we have looked at simple covalent molecules, and they normally only involve several atoms. These are small molecules, and if you remember, they have low melting and boiling points because they only have weak forces between the molecules. Carbon dioxide is an example of this, as is methane. But in today's lesson, we're going to look at giant covalent structures, and these involve many atoms that are covalently bonded together to form large structures. And because they are so large, they have very high melting and boiling points. Examples of these are diamond, silicon dioxide, commonly known as sand, and graphite. So what are the properties of diamond? Well, if we look at the diagram, we can see that all 4 electrons in the outer shell of the carbon are involved in bonding because each carbon atom forms 4 single covalent bonds. And this will affect the properties of this type of carbon. So diamond is very hard. It's the hardest natural substance, and this means that we often use it for things like jewellery and cutting tools. Diamond has an incredibly high melting and boiling point because it needs lots and lots of energy to break the many strong covalent bonds. And because all of the electrons in the outer shell of the carbon are involved in bonding, there are no free electrons, and so diamond cannot conduct electricity. So, graphite is soft and slippery. The layers slide over each other. This is why graphite is used as a lubricant. And graphite conducts electricity. It's the only non-metal to do so. So the free electron from each carbon atom means that each layer has delocalized electrons. These can carry a charge, and for this reason, in science experiments and in the laboratory, you will have often seen that graphite is used as an electrode. Remember that the strong bonds between the atoms, the covalent bonds, are very strong, but between the layers there are weak intermolecular forces, and this is why graphite is slippery. Summarising the differences and the similarities between diamond and graphite then. So they are both made out of carbon, but diamond will make 4 bonds per carbon atom, whereas graphite will only make 3. Diamond is very hard because it has a rigid structure, whereas graphite is soft because it exists in layers with weak forces between the layers. Both of them are giant structures, so will have high melting points. In terms of conducting electricity, diamond does not conduct electricity, but graphite will, and the reason it does this is because it has free delocalized electrons that can move between the layers. This is possible because it only forms 3 bonds, so the spare electron not used in bonding becomes delocalized. They both have covalent structures, and they both exist as big molecules. So graphene is a single 2D layer of graphite. It's made of carbon atoms joined together in a giant covalent structure, and just like with graphite, each of the carbon atoms is covalently bonded to 3 other carbon atoms. So carbon nanotubes have many useful properties. They have a very high tensile strength. They have unique electrical properties and will conduct electricity. And they are good heat conductors. You can have multi-walled nanotubes, and in these several tubes are rotated and slide within each other. And metal atoms can be attached to the outer surface of the tubes. Okay, so we've looked at graphene. Let's now have a look at fullerenes. So carbon can exist in another form. These look like a football, and the first of them, Buckminster Fullerene, was discovered in 1985. So because each of the carbon atoms forms 4 bonds, there are no delocalized electrons. If you remember, to conduct electricity, we need delocalized electrons or free moving ions. So what we can tell is that even though each of the carbon atoms is only joined to 3 carbon atoms, one of those is a double covalent bond, so that each carbon then actually makes 4 bonds. So all of the electrons are used in bonding. Fullerenes are a really exciting area of science that's currently having lots and lots of research in. Scientists believe there will be many, many uses for fullerenes, and here are some of the ones that they've come up with already. So, they use them to make non-stick slippery coatings for machines. Fullerenes are round like balls, so they will roll, which makes them good for lubricating things. They can be used as cages to hold drug molecules. This is brilliant because it means that the drugs could be delivered directly to the specific site of the body where they're needed. Often when we have drugs such as chemotherapy to treat cancer, then all the cells in the body get affected by it. But if you could target just the cancer cells with the drug molecule, then you could really decrease the number of side effects. We could use them as molecular sieves and trap large particles like viruses, but then allow smaller healthy particles to pass through. And finally, they could be used as chemical sponges to soak up toxic substances in the body.